Data centers, AI infrastructure, and investment opportunities. Data centers have become one of the most important forms of digital infrastructure in the modern economy. They support cloud computing, artificial intelligence, AI, streaming services, enterprise applications, and global internet connectivity. As the demand for computing power continues to increase, especially with the rapid growth of AI technologies, the need for data centers has expanded significantly. This paper examines the role of data centers in the global economy, the factors influencing the number of facilities required, and the ways data centers generate revenue. It also explores the economics of operating data centers, including major costs and profit drivers, and analyzes investment opportunities across the industry. Particular attention is given to the impact of AI on infrastructure demand, energy consumption, and future technological growth. The paper concludes that data centers will remain essential to the development of AI, cloud computing, and digital services, while companies controlling compute resources, energy, networking, and infrastructure are positioned to play a central role in the future economy. Data centers are facilities designed to store, process, and distribute digital information. They form the foundation of modern digital infrastructure by supporting cloud computing, artificial intelligence, streaming platforms, enterprise software, and internet communication systems. Nearly every digital service used today depends on data centers in some form. As businesses and consumers increasingly rely on online services and AI technologies, the demand for data center infrastructure continues to grow. This paper examines how many data centers are needed, how they generate income, and the investment opportunities associated with the industry. In addition, the paper analyzes the influence of artificial intelligence on future infrastructure demand and the broader economy. The number of data centers required varies depending on the size and needs of the organization using them. Small startups may only require cloud infrastructure distributed across 1 to 3 regions in order to maintain affordability and scalability. These businesses often rely on third-party cloud providers instead of constructing their own facilities. In contrast, large enterprises typically require at least 2 sites for redundancy and failover protection, along with 3 or more geographic regions to ensure high availability and disaster recovery capabilities. Major technology companies such as Google and Microsoft operate dozens or even hundreds of data center campuses around the world to support billions of users and large-scale computing workloads. Artificial intelligence has dramatically increased the need for advanced data center infrastructure. Training modern AI models requires massive GPU clusters capable of handling enormous amounts of data and computation simultaneously. These AI workloads are typically concentrated in hyperscale data centers designed specifically for high-density computing. At the same time, AI applications used by consumers and businesses create demand for additional regional and edge data centers that can deliver low-latency services closer to users. As AI systems become more integrated into industries such as healthcare, finance, manufacturing, and transportation, the global demand for computing infrastructure is expected to continue rising rapidly. Several major factors influence the number of data centers needed worldwide. One of the most significant drivers is increasing compute demand generated by AI, cloud computing, streaming services, and enterprise applications. Technical requirements such as latency reduction, reliability, redundancy, and disaster recovery also contribute to the expansion of infrastructure. In addition, physical constraints such as electricity availability, network connectivity, and fiber infrastructure affect where new facilities can be built. Governments and regulatory agencies further shape the industry through data sovereignty laws, national security policies, and regional compliance standards that often require data to remain within certain geographic boundaries. Data centers generate income through multiple business models centered around renting infrastructure, computing power, and network access. One of the most common models is co-location, in which customers rent physical space within a data center while supplying their own servers and hardware. The provider supplies electricity, cooling systems, internet connectivity, physical security, and backup systems. Companies such as Equinix and Digital Realty are leading examples of co-location providers. Revenue in this model comes from monthly rack fees, power usage charges, cross-connect fees, and premium support services. Another major source of income comes from cloud infrastructure services. In this model, providers own the hardware and rent computing resources to customers on demand. Services may include virtual machines, GPU computing, data storage, databases, AI services, and networking bandwidth. Major cloud providers such as Amazon Web Services, Microsoft Azure, and Google Cloud dominate this sector. Customers pay based on resource usage, making cloud computing one of the most scalable and profitable areas of the industry. Dedicated hosting represents another business model in which providers lease fully managed physical servers to customers. Revenue is generated through monthly rental fees as well as additional services such as managed IT support, cybersecurity, and disaster recovery solutions. In recent years, one of the fastest-growing segments has been AI and GPU infrastructure. Companies such as CoreWeave and Lambda specialize in renting GPU clusters used for AI model training, inference, and scientific computing. These firms generate revenue through hourly GPU pricing, reserved compute contracts, and enterprise AI hosting agreements. Data centers also generate income through network interconnection services. Some facilities function as internet exchange hubs where telecom providers, cloud companies, and enterprises connect directly with one another. These facilities charge fees for cross-connects, carrier access, and peering agreements. Because network interconnection services are essential for internet performance and connectivity, they are often among the highest margin revenue streams in the data center industry. The economics of operating data centers are heavily influenced by both capital costs and operational efficiency. Major expenses include land acquisition, facility construction, electricity, cooling systems, staffing, networking infrastructure, and hardware such as servers, GPUs, and storage systems. Electricity represents one of the largest recurring costs because modern data centers consume enormous amounts of power. As AI computing expands, energy demand is expected to rise significantly due to the power requirements of GPU clusters and high-density workloads. The primary profit driver for data center operators is high utilization of infrastructure. Facilities that maintain strong occupancy rates and long-term customer contracts are able to generate stable recurring revenue streams. AI demand has further increased profitability by creating shortages in GPU availability and premium pricing for AI computing services. Hyperscale AI facilities may require billions of dollars in construction and hardware investment, but high demand for AI compute resources can produce substantial long-term returns. The growth of data centers has also created numerous investment opportunities across multiple sectors. One of the most direct investment methods involves publicly traded data center companies, many of which operate as real estate investment trusts, REITs. Examples include EQIX, representing Equinix, and DLR, representing Digital Realty. These companies generally offer stable cash flow, dividend income, and moderate long-term growth. Investors may also focus on AI infrastructure firms that specialize in GPU cloud services and high-density AI computing. Companies such as CoreWeave and Nebius represent higher growth opportunities tied directly to AI expansion. Another major investment category includes semiconductor manufacturers that provide GPUs, networking chips, and AI accelerators for data centers. Key examples include NVDA, representing NVIDIA, AMD, representing Advanced Micro Devices, and AVGO, representing Broadcom. Energy and infrastructure companies may also benefit from data center growth because AI facilities require massive electricity consumption and advanced cooling systems. Utilities, nuclear power providers, grid infrastructure companies, and cooling technology firms are increasingly viewed as important parts of the AI economy. Examples include Constellation Energy, and Vertiv. For investors seeking diversification, exchange-traded funds, ETFs, such as SRVR, BOTZ, and SMH provide exposure to digital infrastructure, AI, and semiconductor markets. Despite strong growth opportunities, the industry also faces several major challenges. Infrastructure bottlenecks involving power supply, GPU availability, cooling technology, grid access, and fiber connectivity may limit expansion in some regions. Rising energy consumption has also created concerns regarding sustainability and environmental impact. Nevertheless, the long-term outlook for the industry remains highly positive due to continued growth in AI, cloud computing, and global digital services. In conclusion, data centers have become essential infrastructure for the modern digital economy. They support cloud computing, AI systems, enterprise applications, and global internet connectivity. The rapid expansion of artificial intelligence is significantly increasing demand for compute capacity, hyperscale facilities, and energy infrastructure. Data centers generate revenue through colocation, cloud services, AI infrastructure, and network interconnection, while investment opportunities exist across REITs, semiconductor firms, energy providers, and AI infrastructure companies. Ultimately, the future of AI and cloud computing will depend heavily on organizations that control power, compute resources, networking systems, and physical infrastructure.